Okay, welcome back. I'll share my screen here. Okay. All right, we've now reached the point where I believe I've given you just about everything you need to know to complete assignment number 6 and to complete your compiler project. And so what I'm going to do for the next few lectures is talk about other aspects of compiler design that you may or may not need to, or that you may or may not want to use for your project. But they are important topics, and I really cannot justifiably give a compiler design class without covering these topics. Okay? So any questions at all about how things are going? Assignment 6, where you're generating Jasmine code for some of the remaining control statements. Okay, and then hopefully all these assignments are going to make it fairly straightforward for you to do your compiler project. It's a matter of coming up with a language other than Pascal, unless you're extending the Pascal language, and then that would be okay too. Okay, and remember, coming up with a new language does not mean taking Pascal and just replacing all the reserved words, okay, which teams have done in the past. I really want to see you do something more original, okay? Either a subset of an existing language or invent your own language where you actually have new statements or new syntax for statements. Maybe, let's see, if I recall, the Ruby language had an interesting syntax for the if statement. Okay, so it is possible to come up with different syntax for the common statements, and so hopefully we'll see some of that in your projects. All right, I want to talk about scope. Okay, now you remember how the front end of the compiler deals with scope. It has that symbol table stack, and remember how it looks up variables in that symbol table stack. Okay, so the mechanism that we had defined, in fact, and that question at runtime, we had the runtime stack, and we dealt with scope by at runtime, whenever we encountered a variable at runtime, we needed to know, okay, where is the value of that variable? And that meant we had to look up the appropriate stack frame in order to find the variable's value. And that involved the runtime stack, as you saw here. And we had this runtime display. Okay, so this is all back when we were doing the interpreter, because when we had an interpreter, we were managing the runtime memory, and so therefore we had the stack and all the stack frames and the runtime display and all the backlinks and so forth. Okay, so that's what we had to do. Okay, now this is all based on what's known as static scoping or lexical scoping. Okay, the scope of a variable is determined by how you write the source program, right? If the main program had scope level 1, and then if you had a procedure or function nested inside the main program, that local variables in a procedure or function would have scope level 2, and if a function itself had a nested function, then its local variables are scope level 3, and so forth. Okay, so the scoping is determined by how you write the program, and then when the front end of the compiler is doing a semantic pass, then it's able to determine what is the scope level. Okay, and then of course at runtime, as I was just describing, the runtime values are bound to the variables as determined by the scope, right? you know, if you encounter a variable at runtime, you have to know which activation record contained the runtime value, and the activation record was determined by the scope of the variable, right? This whole point of the runtime display was to point to the topmost activation record of a particular scoping level. So all this stuff about scoping was determined when you write the program. And it's called static scoping. It's static because the scope doesn't change. Okay? Once you've written the program and it's been compiled, if variable I has scope level 2, it will always have scope level 2. Okay? So that's called static scoping. Okay? Now, in C++, we also have static scoping, right? So take a look at this. Okay, here I have int x equals 0. Okay, it's outside of these two functions, f and g, and so then of course it's a global variable, and it would have, you know, scope level 1, say. Okay, and here is a function f, and what does function f do? All it does is it returns the value of x. Okay, and here's function g. Now function g has a local variable x, which it initializes to 1, and then it calls f and returns whatever value f returns. So the return value of g is the return value of f, okay? And f returns the value of x, okay? So the question is, at runtime, what is the binding of this variable x, right? And again, C++ has static scoping. Okay? So what is the value returned by function g? Okay? Does anybody want to venture a guess? Okay. Remember, C has static scoping, just like Pascal. Okay. What is returned by g? Nobody knows? Anybody? Okay, g calls f. Okay. F returns x. Okay, so at this point, what's the value of x?
0.
Okay, and why is it 0? Okay, so the question here is, does this x, is this x the x out here, or is that the x here? Okay, so you're saying f
originally, if x equals 0.
Say that again?
When the g function runs, it's going to return 0.
Okay, when g runs, it's going to return 0. And that is the correct answer. Okay, and why? Well, g returns whatever f returns. Well, what's f returning? Well, f returns the value of x. Okay, now if you know C++ and the way scoping works, this x has to be the global x, right? And so the global x is 0. Therefore, f returns 0, and therefore g returns 0. And the answer is yes, it is 0. Okay. Now, there is another type of scoping, okay, called dynamic scoping. Okay. Now, with dynamic scoping, okay, the scoping is well, with dynamic scoping, the runtime binding of variables to their values is determined at runtime by the call chain. Okay, so with static scoping, you know that the value of x here has to be whatever is the value of the global x, because that's what this x is. This x is the global x. Okay, and therefore the runtime binding is determined by the scoping, the static scoping, and the static scoping says that, well, this x is the global x. Okay, now with dynamic scoping, okay, the runtime binding of a variable to its value is determined by the call chain, okay, not by static scoping. It's determined by the call chain. And the way it works is that at the point where a variable is used, okay, such as here, here we're using the variable. Okay. Well, the way we determine which x it is not by static scoping, but by going backwards in the call chain until we find the first instance where x is being declared. Okay, so that's, and then the value of the variable is the value of the first declared variable that we encountered by going backwards in the call chain. Okay, let's see what all this says here. Okay, so again, we have the same program. Okay, but we're going to pretend that C++ has dynamic scoping. Okay, and so now once again, x, what value is x? Okay, well, here's the call chain. Okay, remember with dynamic scoping, the call chain is important. Main calls G, which calls F. Okay, so at this point, we look backwards in the call chain until we encounter the first time that X is being declared while going backwards in the call chain. Well, inside F, there's no declaration of X. So we go back and G, oh, look, there's a declaration of X inside G. And so this X refers to the X that is declared inside G. Okay? And so with dynamic scoping, then F will return 1 because this X is actually this X, and therefore F returns 1. Well, and then therefore G returns 1 because G returns whatever F returns. So here F will return 1, therefore G returns 1. Okay, so that's how dynamic scoping would work in C++. Okay. Now you may be thinking, well, that's pretty bizarre. What language does it this way? Well, there are languages that do it this way. One that I can think of is Lisp, okay, a language called Lisp, L-I-S-P. If you've never heard of Lisp, don't worry about it. It was a language that came out of the early 1960s. And it used dynamic scoping. And I believe there are a few other languages currently that use dynamic scoping. There are advantages, if you were to compare dynamic scoping and static scoping and list, advantages and disadvantages. Obviously static scoping is a much more common among the languages that we use today. But there are some advantages to dynamic scoping. And so in certain application domains, dynamic scoping makes more sense. Okay? But as I said, static scoping is much more common. Okay? All right, so now you know the difference between static scoping and dynamic scoping. And this little example here illustrates the differences between the two of them. Okay. Any questions about this? Okay. Now, I guess, I could ask, if you are writing an interpreter, which means that you have full control over the runtime, how would you implement dynamic scoping? Let's say that you were going to do a new version of, say, Pascal that uses dynamic scoping instead of static scoping, then what changes would you need to make to the semantic checking pass in the front end, and obviously in the back end, in the executor, you're going to have to make a number of changes. Okay, so something to think about. This would be a good question to ask on an exam. What are the major changes you'd have to make to an interpreter in order to implement dynamic scoping versus static scoping? So something for you to think about. All right, any questions about scoping? Okay, Now, what I want to do today, and I'm the feeling the class is going to end early, but I want to go over the back end, because I gave you for assignment 6, I gave you code for you to finish, but already, even though I left off a bunch of things in assignment 6 in the code for you to complete, there's a lot of code there. And if we look at the architecture, what I did in the back end, okay, let's take a quick look at that. Okay, so oh shoot, again, I forgot to switch the, okay, this will take half a minute. Okay, I'm switching the workspace to the compiler class. All right, so if you look at the back end, you'll see that there are these 4 namespaces under back end. All right, well, here we are. So here's a back end, okay? Here, this is what I gave you for assignment 6. You'll see that there's the compiler, converter, interpreter. Oh, I guess I left off the debugger, which you saw. Okay, well, in the final version, I also have the debugger in here. Okay, so I guess what I gave you for assignment 6 does not have the interactive debugger that I showed you. Did I have it for assignment 5? Let me look in here. Oh no, sorry, that's the Java version. Good grief, that's taking so long to close. Oh, okay. So what I gave you for assignment 5 in the back end did have the debugger. Okay. Now in the final compiler, let's see, the final compiler. Let's see, where is that? That would be Pascal C++. Oh, here it is. Okay. You haven't gotten this yet, but in the final version, I do have all four of them. The interpreter, which is what we started out with, and then remember I added the interactive debugger, and then we did the converter, and then we did the compiler. So here are all 4 of them. Okay. Now you're all working on the compiler, of course. Okay. Assignment 5 was the converter, and now you're finishing assignment 6, which is the compiler, and of course your final project would be the compiler. Okay, so now get back into screen mode here. Now let's see. Okay, now in the back end, there are a number of helper classes, and so if we go back to assignment 6. Okay, there's a label class and there's a directive class. Well, obviously, the whole purpose of the label class is to generate statement labels. And the way I had them, all my labels were L followed by a number. Okay, and so I just kept a variable that increments by 1 every time you want a new label. Okay. And then directive, okay, its purpose is to put out the dot class, dot method, dot field, dot var, dot limit, etc. All the directives, which start with a dot. Okay. So they're not part of the executable instructions, but they were instructions to the Jasmine assembler. Okay, so that's what directive is. So here. Okay, make this bigger for you. Okay, so here under a compiler, we have label, we have directive, okay, and let's see what else we got back there. Okay, local variables. Okay, so local variables. Okay, remember that every stack frame, in the Java virtual machine, has a local variables array. And that's where all the runtime values of the local variables and parameters are kept, for each function. Okay? So I have a class called local variable that helps to keep track of the local variables so that it can put out the well, at the end, it does put out the dot limit locals, okay? But here, it also keeps track of the slots. So whenever we have a local variable and it needs a slot to go into the local variables array, then this class keeps track of the available slots, okay? Now there are parts of the back end that when it determines that certain variables are no longer going to be used, certain local variables are no longer going to be used, usually, quite often it's the temporary variables. And so those slots can be reused by other variables. And so the local variables class keeps track of which slots are being used and which slots are free. Okay. So, and then at the end, it counts up, okay, well, how many slots are actually used, and then it can put out the dot limit locals. Okay. That tells the Jasmine assembler, well, it tells the Java virtual machine that when it pushes the stack frame for a function, because you just called the function, it tells the Java virtual machine, well, how big should it make that local variables array? Okay. And then we have back there a class called local stack. Okay, so again, we see local variables and we see local stack. Okay, now a local stack keeps track of the operand stack. Okay? And so when we're generating code to do operations on the operand stack, pushing and popping variable values and so forth, one of the things that local stack does is it keeps track of how tall that stack ever gets. And so the maximum height is going to be what it puts out for the dot limit stack. Okay? And I did send out a little bug report saying that there is at least one place in the code that I gave you in assignment 6 that I actually got this number wrong. It was 1 too small, and the hack was to just always add 1 to whatever number that dot limit stack directive was about to write out. Okay, that's a hack to get around that bug. Okay. Several students have sent me fixes to that bug, and I need to look over the fixes to see which one is the best one. Okay, but yes, there is that one bug, and that you have to watch out for that. Okay? So as you're generating code, to push values onto the stack and pop values off and so forth, like the add instruction pops off 2 values and pushes 1 value back. You can kind of keep track of, well, what's the tallest that stack can ever get, and then output the dot limit stack, and again, that tells the Java virtual machine how much memory it needs to allocate for the stack. Okay. All right, that's what local stack does. Okay, that class. Okay, there's a code generator. Okay, well, this is the class that it generates the Jasmine code, and it has member variables for a local variables object and a local stack object, which I just showed you. It has emit functions that actually write out the Jasmine instructions. Okay, it can emit directives. Okay. This class will check, when it needs to emit an instruction that refers to a variable. Well, it will check to see if that variable is a local variable, in which case it emits instructions that use slot numbers, or is it a program variable, in which case it emits the get static and put static instructions that actually refer to the variable by name. Okay. But local variables are referred to by their slot numbers, and so emit our code generator knows to look for that. Okay, it knows how to emit code to access elements of arrays and access fields of a record. Okay? And a couple of weeks ago, I was showing you, or last week, I was showing you Jasmine code that deals with arrays and array elements, and Jasmine code that deals with records and record fields. Okay? And so code generator knows how to generate code for arrays and records. Okay? It does some type checking. Now, several of you have already encountered an instance where you had to pass a value to, you had to generate Jasmine code that passes a value to a procedure. And the value that you had evaluated and left on top of the runtime stack was integer, and yet the procedure was expecting a real value. Well, then, of course, you had to emit the I to F command. Yeah, it's the letter I, the digit 2, and the letter F. Okay, that was the mnemonic. And what that command does is it takes the value, integer value on top of the stack and replaces that value with the floating point version. So you have 2 on top of the stack, it will replace it with 2.0, let's say. And so that's something that the code generator needs to do. It needs to look at data types in order to figure that out. Okay. And there are some miscellaneous utilities that do string conversions and so forth in this code generator class. Okay. All right, and we have a class compiler. Okay, and of course, class compiler is where we have all the various visit functions that we're going to override. Okay, and so you can see there are lots and lots and lots of them. And so in compiler, this is compiler.h, and in compiler.cpp is where we actually have all the overrides. Okay? And it's in these overrides that we emit the Jasmine code. Okay? Now, the grammar of Pascal has a lot of rules, and I didn't want all the visit functions to be in one giant source file. So I did break it up. And so compiler has all these visit functions, but the implementation of them has been delegated to 4 other classes. There's a program generator, structured data generator, which generates code for arrays and records, statement generator, and expression generator. And so I just tried to break things up into several files instead of having one source file that has dozens and dozens of visit functions in it. Okay. So let's see. Yeah, so here is compiler. Okay, so here's statement generator. Well, here are all the code emitters for dealing with statements. And so you can see I'm emitting code for an assignment statement. I'm emitting code for a for loop, emitting code for an if statement, and so forth. So instead of putting all this in the compiler class, I pulled it out into a statement generator class just to break up the code. Okay, and there's expression generator, and you can see that there's simple expression. Here's term, and then the factors are things like variables and values. You can see that I emit coding here for arrays, records, integer and real constants, and so forth. Okay, so those are all part of well, this is where code for expressions is generated. Okay. Structured data generator, of course, allocating arrays and allocating records. Okay, and this is what we talked about last week. Okay. Program generator. Okay, this is sort of the top level generator. It generates code for the main program. You can see the epilogue and prologue here. It also generates code for any of the functions and procedures. Okay, that's what here. And we also do some code generation for records. And the reason it's in here is because remember, every Pascal record becomes a separate Jasmine, a separate class in the Jasmine code. It's actually a totally separate Jasmine file. And so I put it in program generator. Okay, it just seemed like the right place to put the emitters for records. Okay. So that's program generator. And okay, I gave you a small excerpt of what's in program generator. Here's emit program. And you can see I go ahead and create a local variables object. And if there are any records, then I go ahead and emit code for records. Here you can see I'm putting out the directives, the dot class public with the program name, and then that dot super has to be every Java class is a subclass of object, and so I have to put out that, and I emit code for the program variables. I emit the boilerplate code for the standard in. I emit code for the constructor of the main class. I emit code for any nested procedures and functions, and then finally I emit code for the main of the program. So you can see that emit program just basically goes through and does everything sequentially, right? And that will end up giving us the Jasmine file. Okay. And okay, here's init main method. Okay, here's the dot main and I don't know how these underlines got in here, but anyway, so this emits the header, emit the prologue, okay, which is the code that sets up the timers and so forth. If there are any arrays and records, okay, I emit code for that. And finally, I emit code for the compound statement, okay, and then I emit code for the epilogue. Okay? So once I've broken everything up into these separate member functions and separate classes, then the code becomes much more manageable. Okay, so here's the main epilogue. All right, well, I emit code to emit the elapsed runtime. Okay, so remember whenever you run a compiled program, it tells you how long it ran. Well, okay, here emitting code that calls the Java timers, and so we get that. And let's see what's going on here. Okay, this is all to print out the elapsed runtime. You can see here that there's a call to the Java's, well, as I said, it's calling the Java timer functions, and these are functions that are in the Java runtime library. So obviously we don't have to write them. All we have to do is make calls to them. Okay. Now you may have noticed these local stack increases and decrease calls. Okay. Remember, local stack is keeping track of how tall the runtime stack will ever get. And so I know that certain instructions will increase the stack size. They push values onto the stack, and certain instructions will decrease the stack size because they pop off values. And so I'm keeping track of all that by letting my local stack object know, and then local stack object will keep track of what's the tallest the operand stack can get. Okay? If I was saying runtime stack, I meant operand stack. Okay, so that's what these calls increase and decrease are doing. It's just keeping track of whether the instructions will increase the size or decrease the size of the operand stack. Okay. All right, and okay, well here's more stuff coming. Okay, here's where we actually print out the elapsed time, and okay, here we are emitting the dot limit stack and dot limit locals, and so we're getting those values out of the local variables and the local stack objects. Okay. So that's program generator. And okay, now for a procedure or function, okay, which I'm just calling a routine, you'll see something very similar. I just go through based on the code template, what code that we have to emit, and see here I'm emitting the header of the procedure or function. I'm emitting any locals, so these are the dot vars that you've seen. If there are any local arrays or records, then I have to emit code that will allocate memory. Okay, that's what's going on here. And okay, here I'm creating a new local variables object. And oops. Now I'm going to go and visit the statement, okay, the body of the procedure or function. Okay, that's a compound statement. You see it's compound statement context, and here I am visiting it, which then of course the various visit functions will emit code for that compound statement, and here I am emitting code for the return from the function. I'm emitting code for the epilogue of the function, okay, which would be the .end method and whatever I need to do to finish off the code for a procedure or function. That will be the epilogue. And okay, here emitting the return. Okay, now if it's a procedure, okay, that means it has no return, not returning a value, I just emit a return. If it's a function, then I have to return the value of the function, which, if you remember with Pascal, the way you decide, the way you specify what the return value is that somewhere there was an assignment statement to a local variable whose name is the same as the function name. And so here, this red code here is just basically identifying that variable that has the same name as the function and getting its slot number so that we can push its value onto the operand stack before we do the return. So this is the emit function that deals with returning from a procedure or function. Okay. And okay, here's the epilogue. Of course, it's just the two dot limit locals and dot limit stack. Okay, and then again, it's the local variables object and the local stack object that keep track of what those values should be. Okay. All right. I think that's it. Okay, so this was a quick and dirty tour of the back end, and now I don't think you need to make any changes to the structure of the back end. But of course, you may need to make changes to the code emitters because you're going to have different statements than, well, you may have different statements than what Pascal has. And so you're going to have to make changes to the code emitter to accommodate the statements in your language. Okay, but I think the overall structure of the back end, you can probably keep pretty much intact. Okay, it's just a matter of making changes within the various classes. Having the code emitters emit different code sequences, based on the grammar of your language. All right, any questions at all? Okay. Looks like there's some chat messages here. Let me take a quick peek at those. Okay, how do we know how to write the compiler visit functions? Okay, so for assignment 6, I gave you quite a bit of code that you can use as a model for how you would finish the visit function. So for example, I gave you code that emits Jasmine code for a repeat state. Okay, so in the Pascal program, source program, you have a repeat loop, and then that gets translated to Jasmine code that will execute the repeat loop at runtime. Okay? So from that, you should be able to write the visit function for a while loop, because while loop is not that different from a repeat loop, and so you should be able to generate code for a while loop. Okay, and then going from while loop, I would say the next thing you might want to look at is how to generate code for an if statement. Okay, well, remember in my slides, I given you a number of code templates that basically outline what code you should be generating for each of these statements. Okay, so I would say that after you've done the while loop, okay, you should be able to do the if statement. Okay, now making calls to a procedure or function. Well, remember, in order to call a procedure or a function, you first have to evaluate the arguments of the function and leave their values on top of the operand stack. Well, then you emit Jasmine code to evaluate each of the arguments. Argument is some sort of expression. Could be as simple as one variable or a constant, or it could be an arithmetic expression. So you generate code that will evaluate each of the arguments and leave its value on top of the stack. And then once you have all the values on top of the stack, top of the operand stack, you can then generate a Jasmine code to actually call the function. Remember, that was an invoke static instruction that will then call the function. And then right after that, if it was a function and not a procedure, the function would have left the return value on top of the operand stack, and then you generate whatever, after the code to call the function, you generate whatever code you need to make use of that return value that's sitting on top of the operand stack. Okay? So that's basically how you know how to write these visit functions. You use the ones that I've given you as a model, such as looking at repeat in order to do while, and then looking at the various code templates that I've given you that basically shows you for each of the various statements what the code should look like. Okay. All right. Okay. And any other questions about this? Okay. Hopefully a bit long-winded here, but hopefully I answered the question about how you know how to go about writing a visit function to emit Jasmine code. Okay. You basically look at the ones I've already given you as a model, and make use of the code template diagrams that are in my slides. Okay. Okay. And any other questions? Okay. Now, as I said, if you successfully can do assignment 6, then the compiler project should be fairly straightforward. You will have a different language, a different grammar, but we're sticking with procedure-oriented languages. So you're going to have assignment statements and if statements and compound statements and while loops and so forth. And so you just have to make the necessary changes in the back end to accommodate your new language. But I would think that once you've done assignment number 6, 85 to 90% of the work is done. Okay, and it's just that remaining 10% because you've changed the grammar. Okay, you'll have new visit functions potentially. I mean, it depends on how you name the all of your non-terminals. Depending on how you wrote the grammar, you'll have some different visit functions that Antler generates for you. But in order to override those visit functions, you have example code that you can use for writing your overrides of the visit functions. Okay. So definitely make good use of the code that I've given you for assignment 6 and use that as a model for how to finish the remaining visit functions, and then you'll be able to do your project. Any other questions? Okay. I know that this is a very difficult class, and I know that unfortunately it's the last class of, well, it's during your last semester, so you've got your senior projects and everything to worry about, but I try very hard to make everything manageable. So if you think it's not manageable, then maybe you've gone down the wrong path. So let me know, and hopefully I can steer you back onto the right path. Okay. All right, if there are no questions, use the discussion forum if something comes up, and I will have my office hours starting at 4:30. So, all right, then I'm going to stop the meeting, and we will see each other again next week when I will talk about other aspects of compiler design that you may or may not need for your projects, but are still important to know about. Okay. All right. Thank you for coming, and we'll see you next Tuesday.